In this video, we will solve the problem of finding lowest common ancestor of two nodes in a binary tree. So let's first understand what is a lowest common ancestor. So suppose we are given a tree, say 1, 2, 3, 4, 5, 6. So in this tree, if we have to find the lowest common ancestor of 5 and 6, then it is the lowest common ancestor of 5 and 6 is 3. Why? Because if we move upwards from 5 and 6 towards the root, the first common node is 3. So that's why the lowest common ancestor for 5 and 6 is 3. Similarly, for 4 and 7, the lowest common ancestor is 2. Similarly, for 2 and 3, the lowest common ancestor is 1. Similarly, for 4, say suppose we are taking 4 and 6. For 4 and 6, the lowest common ancestor is 1. Why? Because when we move from 4 towards the root, and also simultaneously when we move from 6 towards the root, the first common element which we encounter is 1. So that's why 1 is the lowest common ancestor for 4 and 6. Similarly, 1 is the lowest common ancestor for 7 and 5 as well. So this is what is the meaning of lowest common ancestor. So in this problem statement, we'll be given two integers, okay, and one binary tree, and we have to find the lowest common lowest common ancestor of these two integers. Basically, these integers are nothing but the node values. So now let's understand how we are we gonna find it. So suppose this is the binary tree which is given to us, and these are the values 1, 2, 3, 4, 5, 6, 7, and we have to find the lowest common ancestor of, say, suppose 4 and 8. So we have to find the lowest common ancestor of 4 and 8. How are we going to do this? So this brute force solution would be we will find the path from root to 4, right? We can do that. We can find the path from root to node 4. What is the path? Path to node 4 is 1, 2, 4, right? We can do find this in order and s- space complexity and order and time complexity, right? And then we can find the path to node 8. What is the path to node 8? 1, 2, 5, 8. And this also we can find in order and time complexity and order of n space complexity. Then after that what we can do is we can iterate through or traverse through these two vectors until and unless we find a different node. So first we will see what is there at the zeroth index. So at zeroth index we have 1 which is common, which is same in both the vectors. So we'll move forward. At index 1 we will see 2 is there in both the vectors. So we'll move forward. Then we'll see at index 2 we have 5 in this vector and 4 in this vector. So this is different. So it means that 2 is the common node in these two vectors, and that's why 2 is the lowest common ancestor of 4 and 8. But here we are taking some extra time and extra space, right? So we can avoid this extra space and extra time which we are doing in this brute force approach. So how can we optimize the solution? Let's think about it now. I'll just take this example and try to come up with a better approach. So now before that, let's first list down the cases, different types of cases that we can encounter. So case one is that when we iterate through the nodes of the binary tree, we encounter a node which is same as we encounter a node which is same as one of the integers which we are looking for. Suppose we are looking for LCA, lowest common ancestor of 2 and 8. Okay, so in this case 8 is in the right subtree of 2. It means that 2 is the LCA here, right? 2 is the lowest common ancestor because 2 is the ancestor of itself and 2 is also the ancestor of 8, right? So that's why 2 is the lowest common ancestor of 2 and 8. So case 1 is any one of the given integers itself is the lowest common ancestor, right? Case 2. Case 2 is that any other node, any node, it can be any node or a node having one integer in left subtree and one integer in right subtree, right? For example, let's take LCA of 4 and 8, right? So L4 is present in the left subtree of 2 and 8 is present in right subtree of 2. So that's why 2 is the lowest common ancestor of 4 and 8, right? So this is the second case. So now we have to visit through the binary tree using depth first search traversal mechanism, and we have to find the lowest common ancestor of the given integers. Now for that, what we can do is we can use a divide and conquer kind of approach. Not exactly divide and conquer, but you know, going towards the leaf nodes and then finding the trying to find the lowest common ancestor and then making the solution bottom up, right? So we have to find this, we have to follow this bottom up approach here. So what we are going to do here is we will try to see, we'll start iterating from the, we'll start traversing from the root, we'll go down, we'll check if 4 is an LCA, yes or no, backtrack, come here, we check if 5 is an LCA, yes or no, backtrack, check if 2 can be an LCA or not, backtrack, so on and so forth. Visit every node and check whether is it possible that it can be an LCA or not based on these two conditions, case 1 and case 2, right? So for that, how our algorithm will look like, we will have a helper function which will return the node, which is basically the lowest common ancestor node, and will pass to it the root, the x element x and element y. If root is null, definitely it cannot be an LCA, correct? So we'll just return null if root is null. Second condition is second condition is if root's value is equal to x or y. So in that case, we have encountered case 1 here, right? Any one of the given integer itself is the LCA. So there is a possibility that if root's value is equal to x, there is a possibility that y is present in the subtree of x, right? There is a possibility. So we will return root here. Now we have to see case number 2. That is, a node can have one integer in left subtree and one integer in right subtree. So for that, what we have to do is we have to create a node pointer L, and which is equal to roots left x comma y. So it will basically find out whether any of these integers x and y is present in the left subtree of the current root node or not. Similarly, there will be one more root node pointer r, which will find if any of these elements is present in the right subtree of or not. If both L and R is not null, it means that one of the elements is in the left subtree of this root node, another element is in the right subtree of this root node. So that's why we will return root. Root will become the LCA, right? Other condition is if suppose one of them is null, right? If suppose left is null, then we will return R. Why we will return R? Because there is a possibility of the first case now. Case 1. Any of the given integers itself is the LCA. So, suppose in this case, no, we will just return R here. Why will we return R? Because there is a possibility, like suppose there is, let's take an example. We have to find LCA of 5 comma 6 in this tree. Okay, so one if what will happen is when we will come here and we'll see that okay, roots value is equal to x, we'll return root here, right? We will return 5 here, and here at 2 we'll return null from here because nothing is, it's not equal to x or y. 4 is not equal to x or y, so it will return null. It will return 5. Now we have to return the valid value here, which is not null, to back to 1. Then only what will happen, there is a possibility that this 1 has another node in its right subtree, correct? So similarly 6 will be returned back here and 6 will be returned back here, and ultimately we'll get okay, we'll encounter this condition if L and R for this root, right, for this root, and we'll return the root 1 as the answer. So that's why whichever value is not null will return that. So else if R equal to null, return L. So this is how it will work. We'll do a dry run and see how our algorithm will work on a binary tree. So this is the binary tree given to us. Suppose this is 1, this is 2, 3, 4, 5, 6. We have to find the LCA of say 4 and 6, right? 4 and 6. So now what will happen, we will call this function helper with the root pointer. So currently root is equal to 1, x is 4, and y is equal to 6, correct? We'll come here, we'll check if root is null. No, it's not null. We'll not go inside this condition. If root's value is x or y is equal to x or y, no, it's not true. We'll come down. We- Now we will see, evaluate these two pointers, value of these two pointers. So L will be equal to helper of roots left, so that is 2, correct? So we'll come at 2, we'll check if root is null. No, root is now 2. Okay, we'll check if root is null. No, root's value is equal to x or y. No, we'll come back. Sorry, we'll now evaluate again its left child. So L is equal to helper 3. Now we'll see if root is null. No, 3 is not null. If root's value is equal to x or y, no. Then again we will evaluate L and R for root 3, node 3. So L and R both are null, right? Both are null. So we will return null back from here. Since both are null, we will return null back from 3 to 2, right? Now we will go back to, so this L is equal to basically null. Helper 3 will return null back to 2. Now we'll come here to the right side, to the right subtree, and we'll call helper 4. So 4 is equal to x, right? So that's why we will return 4 here. So this will return 4. Now we'll at no for node 2 we will check if L and R both are not null. No, this is not true. L is null, correct. L is null, so return R. So this 2 will return R, which is equal to 4 to the node 1. Now for node 1 we have computed, so this will be equal to 4. Now we'll see what is the value in its right subtree. So helper, we'll call helper 5. Helper 5 will in turn, helper 5, so root becomes 5 here, and we have called helper 5. So helper 5 will return, will first check if it is equal to x or y. No, it is not null as well. So these two conditions don't are not true. Now we'll evaluate its left subtree has any of these elements or not. So we'll call L equal to helper 6, right? So now this root, this has now become the root. So root's value is equal to x or y. Yes, it is true because root's value is equal to 6. So it will return root. So it will return 6 back to 5. Now we'll see the R side. Right side is null. Right side is null. It doesn't have a right child. So in turn, this value will be null. Whatever R equal to helper we are calling here, R equal to helper null will return null, and this L equal to helper 6 will return 6 as we saw here. So now for 5 we will check the condition if L and R both are true or not. Since both are not null, I mean one of them is null, we cannot return root here. What we'll do, if L is null, return R. L is not null here. If R is null, return L. Yes, right is null, so that's why we will return 6 back to 1. So for 1 we will check this condition if both L and R are true, so return root. Yes, if L and R both are not null, return root. So for root equal to 1, we got L equal to 4 and we got R equal to 6. Since both are not null, we will return 1 and this will become our LCA. Now let's write the code for this solution, for this problem. So let's first go through the constants. The number of nodes in the tree is in the range of 2 raised 2 comma 10 raised to 5. So we can have a have an integer variable to store the values or for calculation. Minus 10 raised to 9 and 10 raised to 9 is the range for node values. That is also fine. We can again use integer. All node values are unique. P is not equal to Q. So these are the two nodes P and Q given to us, and P and Q will exist in the tree, and all nodes are unique. So definitely these will exist. So now what we have to do is we will use a recursive helper function for our solution. So we'll just directly use the helper function and pass the root, the p and q to this helper function, and this helper function should return the lowest common ancestor node. So we will the return type will be a pointer, node pointer, and let's pass these three parameters here. Now, if root is null, it means it is not the LCA definitely. So we will return null. If roots val is equal to p's val or roots val is equal to q's val will return root. Since we have encountered one of the nodes, we are returning that particular node. Otherwise, what we have to do is we have to see if the nodes exist in the left subtree or right subtree of the current root node or not. So we'll pass tree node pointer. We'll do tree node pointer. We'll will compute we'll get the value of left subtree with this function helper roots left, and now we'll get the check if whether any node exists in the right subtree or not with this function. We'll pass the right child of pointer to the right child of root here, and if L and R both are not null, L is not equal to null and R is not equal to null, we will return root. Since both are not null, it means that the root is the lowest common ancestor, because one of the elements is present in the left subtree and the another element is present in the right subtree. If not, if L is not equal to null, return null. So we have encountered, sorry, return L. So one of the elements is there in left subtree, so we'll just return that. Else, if R is not equal to null, return R. Otherwise, if nothing is present in the left or right subtree, then just return null. So we'll run this solution and see if we got the correct answer or not. There is some problem with the network. It's saying reload the page. Okay, now let's run it again. This is accepted, and let's submit the code and check whether it passes. Yes, it passes all the test cases. Now let's find the space complexity and time complexity for this solution. The space complexity would be big O of n, which is it is basically equal to the height of the recursion tree, right? So the maximum height of the recursion tree in worst case is big O of n, where n is the number of nodes in the tree. So that is our space complexity, and the time complexity is, since we are traversing each node exactly once, the time complexity will be big O of n. So thanks for watching this video. If you have any doubt, please comment in the comment section. Thank you very much.